Hello everyone. Welcome to the video on power system 2 subject. In the module 3, we are going to see about the per unit system and load flow analysis. In the today's lecture, we are going to discuss the power flow equations. Myself Ganesh, working as assistant professor in electrical engineering at Kekewag Institute of Engineering Education and Research, Nashik. So let's see what are the content of the today's presentation. The first one is the necessity of load flow analysis. What information you will get from the load flow analysis. Then how you classify the power system buses. Then power flow equation for 2-bus system and power flow equation for n-bus systems. So these are the content of the today's session. And the last is summary. Okay, let's begin with the learning outcomes. What are the learning outcomes of the today's session? At the end of this session, the learner will be able to elaborate the necessity of load flow analysis. Why the load flow analysis is necessary and what information you will get from that load flow analysis will be described at the end of this session. Then how to classify the power system buses. Based on this, how we are going to classify the power system buses. Then recognize the importance of load flow studies in the power systems. So you should be able, learner will be able to recognize the importance of the load flow studies in the power systems. Then derive the load flow equation for 2 and n bus systems. Okay, so at the end of this session, these four of the outcomes we are going to achieve. Let's see what is the first. We will begin with the first question. Here is the reflection point. Here I am going to ask one MCQ to you, multiple choice question. There will be 4 options. You have to choose the correct options. Okay, so after displaying the question, you pause the video, you write down the answer, and you cross check that answer with me. Load flow analysis in power system is used to determine, first one, steady state operating point at a given load. Second, dynamic operating point at a given load. Third, transient operating point at a given load, and any of this. Okay, so pause the video and guess the answers. So it will enhance your learning and understanding. Yeah, hope you have answered the question. So let me give the answer of this question. Here the answer is what? Just a minute, I will take a point. Here the answer is what? Steady state operating point. The load flow is going to determine the steady state operating point at a given load. For a given load, how much is the generation, how much is the line flows at a particular load, that is a static point, it is going to be determined. It is not a dynamic operating point or it is not the transient operating point. Hope you have understand this. So let me clear this. Let's come to what is the necessity of load flow studies, or oftenly it is also known as the power flow studies. Okay, both are the same in the power system, load flow studies or power flow studies. So load flow terminology, this terminology is used for the flow of power from one or more sources. It is used from one or more sources through available path to the load. Let us take example. I have a generating station with me at my end. Suppose I am in Maharashtra in Nashik. So I have this one generating station. I have another generating stations at the Chandrapur, and my load point may be at the Chandrapur, some local load points at the Chandrapur as the at the Nashik. So this is plant at the Nashik. This is plant at the Chandrapur, and this is let the load is at Pune. Okay, so load point is at Pune. So this is what load is at this bus. Similarly, there may be a local load at this Nashik bus. Okay, so there may be a local load at this bus. These all are interconnected through the transmission lines. Okay, so these buses are interconnected through the transmission line. For a time being, I can consider this is a 3-bus system. So if you observe this, this is a 3-bus system. It is connected through the transmission line. So this is in terms of single line diagram representation. In the power flow, what is the contribution of this generator? What is the contribution of the generator? Fill this all loads through the possible path. The current may be power may flow from this path to this path, or reverse also, this path to this path, this path to this path. Okay, so how, which generator is supplying how much low, how much power, that we are calculating in the load flow analysis. Hence this is also known as the power flow or load flow analysis. What is the necessity? It used to determine the direction of power flow. Okay, direction of power flow on the single line diagram. For radial system, so let us consider that there is a radial system, that is one generator feeding to the subsequent loads. So this is the radial systems. This is one transmission line, this is another transmission line, this is another transmission line. It radial flow is, these are the loads are here. To determine the load flow analysis in the radial, it is a very easy, but to determine the load flow in the interconnected systems is become very difficult. So let me erase all this. So for radial, it is power flow may be very simple. Today's interconnected system is the more complex, having the number of branches and number of buses. It act as the circuit as long as the circuit remains unchanged. So if the circuit is remain going to constant, then power flow will not be changed significantly. But if the circuit is not going to be constant, then power will be changed. Then the power flow will be changed. So as long as circuit is balanced, circuit is unchanged, the system is also balanced. As a circuit configuration changes, power flow is also changes. In practice, yeah, this is a very true statement. This is not in the hand of the power supply authority. Load is never constant. It changes from time to time. It changes from time to time. Hence, power system planner, that is the power system engineer, means us, we have to see the future requirement and allow the additional changes, or what are the additions and changes are required in the existing system. That can be decided only through the load flow analysis. Okay, hope you got the necessity of the load flow analysis. So for this all, we need to calculate the load flow analysis in the software purpose. So what information you will get from the load flow analysis? So let's begin with the diagram. In the power flow or load flow analysis, the inputs are line data, means transmission line data, then bus data, information of the bus, whether that bus is connected to the generator or load, or it is the voltage control bus. Generator and load data, what is the generation is available, what is the load at the particular bus, that is the input to a particular bus. And for that particular bus, through the power flow analysis, we are going to determine the voltage magnitude, we are going to determine the power angle, we are going to determine what is the real and reactive power injected at that bus, what is the current flow, and what is the power loss at between the two buses. Okay, so that information you will get from the load flow analysis. So let's see what are the information we are getting. Steady state operating point, obviously it gives the voltage magnitude and phase angle. It gives a line flow. So what is the power transmission through the lines? Suppose this is the two bus systems, so it is interconnected by, system is interconnected by the two bus systems. Let this is another generator over here, and let there are the local load point at this end and this end also. So what is the line flow? What is amount of the line flow in the direction of the power flow? Active power P and reactive power Q through this line. Okay, so what is the power flow through this line? That is in terms of megawatt and in terms of MVAR. Then real and reactive power supplied by the each generator, how much each generator is contributing the real and reactive power. Then in between there may be a transformer, so what is the loading of that transformer, it is also equally important, that we will get the information through the load flow analysis. It also gives the overload condition as poor voltage existence, at which bus we are having the low voltage point, that is also possible to get, means it is overloaded bus. So that can be possible. Then angle separation between these two buses, suppose this is the sending end bus, so it is a Vs at an angle of delta, and this is what Vr at an angle of 0. Means this angle separation, that is a delta angle, is nothing but the difference between these two. This delta angle information you will get. Then power system planning in dispatching and allocation of generator. So for meet the particular demand, which generator should be connected, which generator should be disconnected, that information is also possible through that is dispatching and allocating the generating units, that is possible. Then optimal allocation of the capacitor and their sizes to improve the stability. So suppose voltage at this bus is going to low side, then how much capacitor will be added to that at this bus to improve the voltage and to improve the stability of the systems. So that study can be possible by getting the information through the load flow analysis. So by this way, we will get the load flow, we will get the information about load flow analysis. Okay, so let's see. So hope you understand what is the importance of the load flow and load flow studies. Here again the reflection point 2, I'm going to ask the second question to you. Okay, it's the time of KBC. Okay, so kaun banega crorepati. So let's begin with the second question. If equation have a trigonometric terms, then type of equation, here I'm going to give you 50-50. Okay, so in the KBC we have 50-50, so I'm going to give you 50-50. Okay, so there are only two options. If the equation have a trigonometric terms, then what is the type of equation is? Okay, linear equation or non-linear equation? Pause the video, answer the question and tally that answer with my question. Yeah, hope you got the correct answer. Obviously it is what? Non-linear equation. Okay, so because it is having the trigonometric term. Okay, which is the linear equation? In which the variable have a single power. So suppose x variable and y variable, it is raised to 1. Okay, so it indicates that these terms are what? Linear equations. But in the non-linear equation, suppose we have a cosine term, suppose we have a sine term, or x square term, y square term, then it is called as the nonlinear equation. Why I'm discussing this? Because all the load flow equations we are going to see of which type. Okay, so let's begin with the basic of the power flow equation. The power flow equation is a set of nonlinear algebraic equations. So it is not a linear equation, it is the nonlinear algebraic equations. Hence we have to apply the methods of solution of nonlinear algebraic equation. Then power flow equations are basically expressed in real and reactive power at each bus. For suppose this is the bus number I. So for this bus number I, okay, suppose it may be generator bus, it may be load bus. So at this bus number I, what is the active power injected and what is the reactive power injected, that is going to be calculated. That is a PI and QI. So it is so for each bus we have equation of PI and we have equation of QI. It is nothing but a power flow equation. Real equations with the voltage either in rectangular form or polar form. So this PI equation and QI equation is in terms of voltages, means this PI. Okay, so this PI equation is the function of magnitude of voltage and angle delta. Magnitude of voltage and angle delta. So this angle voltage and delta. Okay, so this angle voltage and delta. So this equation may be in the polar form. Okay, so it may be in terms of magnitude and angle, or it may be in the rectangular form. Okay, so it may be in rectangular form, means real and imaginary form. So both things are possible. So to derive these equations, we need a Y-bus matrix. Why we not using Z-bus matrix? So suppose the two buses are not connected with each other, then impedance between them it is infinite, and in Z-bus many terms of the infinite terms will occur, and that will cause uh, lots of mathematical error in the systems. So if the two buses are not connected, means impedance is infinite, but admittance between these two is 0. So we know that Y-bus matrix is the sparse matrix, means there are many entries. Many entries are the zeros entries, so it is called as a sparse matrix. So it is a sparse in structure, so it will give you the fast solution due to the only handling the non-zero entries, and also the memory requirement will be less. We will discuss in the detail in the load flow analysis. So let's begin with the methods of load flow analysis. So begin with the variables in the power systems. So there are the four variables in the power system: active power, reactive power, voltage, and angle delta. Magnitude of voltage and angle delta. Suppose this is the bus number I, so I can say it is a PI, QI, VI, and delta for ith number bus. I'm talking about the ith number bus. So for the ith number bus, it may be PI, QI, VI, and delta. Out of this, two quantities are known and two quantities are unknown. What are the two quantities known and two quantities unknown? We will see in the next slide. So the variables in the power system, some variables are uncontrolled variables, which is also called as a disturbance variable. So what are the uncontrolled variable? demand. At a particular bus, what is the load connected? That load is not a controllable variable. Load is uncontrolled variable or disturbance variable. So because it is going to be changed at every moment of the time. So this is the uncontrolled variable. Some variable are the dependent variable. So dependent variable are the nothing but the controlled variable. That means suppose ith bus is connected to the generator, the power supplied by this generator, active power, and reactive power supplied by this generator, that is a QG, these are controllable in nature. So as these both are the controllable in nature, so we can call it as this as the independent variable, because they are not depending on the any other quantities. Okay, so then the dependent variable is a V and delta, because the voltage is depending upon the reactive power, and the delta angle is depending upon the PG, that is active power. Hence this V and delta, these are the dependent variable, which is also known as the state variables. So mainly power systems, so these two variables may be controlled or uncontrolled depending upon the type of bus, whether it is a load bus or whether it is a generator bus. And this V and delta, it is a state variable of the systems. Okay, so let's begin how we are going to classify these buses. Okay, so the next part is the classification of buses. So there are mainly three types of bus: PQ bus, PV bus, and V delta bus. In the PQ bus, it is also known as the load or generator bus. Load or generator bus. For the load or generator bus, P and Q are generally known. Generally, P and Q are known, so V and delta are unknown. Suppose such numbers of n1 number of buses, I have n number bus systems. So in that bus, I have n1 number of buses. N1 buses are the load buses or generator buses, which is also known as PQ buses. Sometimes this generator buses is also come in the category of voltage control bus. Why? I will discuss with you, because now the modern generators have a faster voltage control, means it gives the constant voltage. So we can treat the generator bus in the voltage control bus also. So next bus type is a PV bus. In the PV bus system, the active power and voltage is the known quantities or specified quantities. Active power and bus at voltage at that bus, that is the magnitude of the voltage, is known. So what is the unknown? Q is unknown and delta is unknown. So that is to be determined, means two quantities are known, two quantities are unknown. Such number of buses in n number of bus systems, suppose such buses are n2 number of systems, and we have to take one bus as always reference for the all the calculations, and that is known as the slack bus or swing bus. So what is the slack bus or swing bus? The ability of this bus is what? Angle voltage and delta is equal to 0, but the voltage is generally taken as a 1 pu. Okay, generally taken as a 1 pu voltage, and voltage and angle delta is taken as a 0 because it is a reference bus. For that bus, this bus is capable to supply the infinite P and infinite Q. That is, this is able to supply the required, all remaining required active power and reactive power. Such bus is only one in the system, and generally in n bus system, the bus number 1 is called as the slack bus or swing bus. Okay, in the slack bus, as the delta angle is 0 and V is 1 pu, its voltage and angle is always fixed. It is able to supply the required infinite active, and it may be supply any amount of P and Q to that bus. So hence it is a reference bus or slack bus. Okay, so this such type of bus, there is only one bus in the system, which is generally bus number 1. So total number of buses are PQ buses, PV buses, and slack bus. So total number of buses. So in n bus system, one bus is always slack bus. There may be existence of PV bus or PV bus may not be exist. Maybe all buses are PQ. Okay, maybe all buses are PQ. Only PV buses are not possible. Okay, so either buses are slack bus plus PQ bus, or slack bus plus PV bus plus PQ bus. Okay, hope you got this idea about the classification of buses in the systems. So based on this, I have a reflection point at the next. So this is my reflection point 3. Bus with the synchronous generator with fast excitation systems. Okay, so let us consider that there is a bus which is connected with the um, uh, bus is connected with the generator, synchronous generator, having the fast excitation system. Such type of bus is called as PQ bus, PV bus, slack bus, or swing bus. Okay, pause the video and answer this question. Hope you got the answer. So it is a fast excitation system, means it is able to keep the voltage constant at the terminal. So voltage is the constant and P is also constant for that. So it is generally known as the PV bus or voltage control bus. Synchronous generator with fast. So modern power, in the modern power system, all synchronous generators are connected with the fast excitation system. That is the generally it is using the static excitation system, which is very faster. So having the lesser time constant, so that bus nowadays, that bus can be treated as a PV bus, not as a PQ bus. In the old days, when there is a slow excitation system, that buses was treated as the PQ bus. So hope you got this answer. Let's come with the next reflection point. Okay, how you are going to calculate the complex power in the power systems. Okay, so I'm giving you the four options. The first option is complex power S is equal to V into I. Complex power S is equal to V conjugate into I. Complex power S is equal to V conjugate into I conjugate. Complex power S is equal to V into I conjugate. Okay, so pause the video for some duration and answer this question. Come on, come on, come on. Yes, hope you got the answer. So here there are two options are right, V into I conjugate and V conjugate into I. Suppose you take the V conjugate into I, that power will become as P minus JQ, where minus JQ indicates that it is the reactive power, it is the inductive reactive power, and plus JQ indicate that capacitive reactive power. Okay, here it is P plus JQ, where the plus JQ indicates inductive reactive power and minus JQ indicates capacitive reactive, or just exactly opposite. So here minus indicate inductive reactive power. Okay, so Q is in terms of inductor, and plus indicate it is the capacitive reactive power. And here the plus indicate it is the inductive reactive power, and minus indicate capacitive reactive power. Okay, so it is XC, capacitive reactive power. So generally we are in India, we have adopted that S is equal to V into I conjugate. In the some country they are taking V conjugate into I. Okay, so we from henceforward we will consider that complex power S is equal to V into I conjugate. Why this is S in V into I conjugate, you can see in my next video or forthcoming video. So I'm going to discuss why this complex power is V into I conjugate. Okay, so let me erase all this whatever I done. Okay, let's come to the power flow problem. I am going to derive the power flow equation for two bus systems. So let us consider that this is a generator 1, this is a generator 2. I am having the two bus, the bus number 1 and bus number 2. The bus number 1, the generator is connected to this bus number 1, who is generating the complex, who is generating the apparent power as SG1, in which PG1 plus JQG1. The load which is connected, that is the demand of that bus, is SD1, which is nothing but PD1 plus JQD1, active power and reactive power load at that bus. Similarly, at bus number 2, the generator 2 is supplying the SG2 as the apparent power, which is equal to PG2 plus JQG2, and the demand at this bus is SD2 is equal to PD2 plus JQD2. And these two buses are connected through the transmission line. Let the reactance, or I can say the impedance of this transmission line is Z. Okay, so impedance of this transmission line is Z. So I can write down the power which is at the bus 1 is equal to Pg1 minus PD1, that is because this is the generation, this is the demand. So Pg1 minus PD1 plus J Qg1 minus Qd1. This is the power injected at this bus. Similarly, power injected at bus 2 is equal to Pg2 minus PD2 plus J Qg2 minus Qd2. So this is the complex power equation in the two bus systems. So let us put in this single line diagram in terms of the network diagram. So this transmission line can be modeled as the pi model. So this is the Y12, that is a transfer admittance between these two buses, and this is what self admittance of these two buses, Y10 and Y20. In the Y bus video, you might be come across this such Y bus matrix. Let generator 1 is injecting the current J1. Okay, so that is S1 power is injected, that the current injected at the bus 1 is J1, and the current injected at bus 2 is J2 by the generator S2 with respect to the reference bus. So this is what my network diagram from the single line diagram. So this is the modeling diagram. So let's come to the to derive this equation. Okay, so if I apply the KCL at this point, okay, so KCL at this point, so current injected is J1, is equal to, what is the outgoing current? So let us consider this is the outgoing current, this is the outgoing current. So what is the current flowing through this? This is the Y10. So Y10 into V1 is the current flowing through the reference. Then what is the current which is going from here? It is Y12 V1 minus V2. So suppose we bring the terms V1 and V1 nearby. So it will become Y10 plus Y12 into V1 minus Y12 into V2. Similarly, at bus 2, we will apply the KCL to get the J2. Okay, so J2 is equal to Y20, the current and bus voltage at this bus is V2. So this is the V2 into Y20 plus Y12 V2 minus V1. That is, from this we will bring the terms of V1 and V2, we will separate that term. So V1 is equal to minus Y12 V1 and plus Y20 plus Y12 V2. I will put this into the matrix form. So J1 and J2 is Y10 plus Y12 minus Y12 minus Y12, Y20 plus Y12 V1 and V2. So I will call this as the self admittance, that is a Y11. I will call this term as the transfer admittance, that is Y12. Okay, so again this is the transfer admittance and this is the self admittance of bus number 2. Okay, so hope you know this. We have already studied in the Y bus matrix. So in general, I can write down this equation in terms of mathematical equation. I can write down the current at the ith bus is the summation of k varying from 1 to 2 yik vk. Let's expand this equation. So yik, k is starting from 1, so it will become y. Suppose this is I is equal to 1, so this will become a 1. So y1k, k is equal to 1 first. So y11 v1 plus, then k will become a 2. So y12 v2. Okay, so means we are getting this equation. Okay, so in this form, so y11 v1, y12 v2. Okay, so this is what equation we are getting. Okay, so this is the equations which we are getting. Now the complex power. Okay, so we know that the complex power at the bus 1 is P1 plus JQN, and we in the reflection point we studied that it is nothing but V1 into J1. The J here, it is a current which is injected at that bus. So V1 into J1 conjugate. Similarly, S2 is equal to P2 plus JQ2, that is V2 into J2 conjugate. I will take the conjugate of S1 and conjugate of S2. So if I take the conjugate of S1 and conjugate of S2, this will become P1 minus JQ1, P2 minus JQ2. That is V1 conjugate, V2 conjugate, and here J1 and J2 will not be taken as a conjugate, is taken as a plane. Okay. So the complex power at the ith bus, from this equation, how I'll get the complex power at the ith bus? Complex power at the ith bus is equal to Pi minus JQi, which is nothing but Vi star into Ji. Actually, this term is what? Ji. But in the previous section, we studied that this is what? Yik into Vk. So Ji here, the Ji is replaced as Yik into Vk. K is varying from 1 to 2 because there are two number of buses. Okay. Hence, SI conjugate, that is Pi minus JQi. What is the Vi? Vi is generally it is at an angle of delta I. And Vk, it is generally at an angle of delta K. And Yik is taken as mod of Yik at an angle of theta ik. So what is its significance? I will tell you in the impedance matrix, admittance matrix. In the admittance matrix, suppose this is what G, conductance, this is the susceptance, then this is a Y, and this is what angle? Theta. So same I am taking here, okay. But suppose if you take it is a GIK plus JBIK, that term will be in rectangular form. Okay, this is in polar form, that term is in rectangular form. Same I have substituted here. I want to take the VI conjugate. Suppose you want to take the VI conjugate, then this angle will become a minus delta I. So mod of VI at an angle of minus delta I, YIK at an angle of theta IK, and VK mod of VK into angle of delta K. VK is not taken as a conjugate, only VI is taken as a conjugate. Okay, so I bring this delta I term inside this, so that will become theta ik plus delta k minus delta I. Then I will remove this conjugate term. Suppose the conjugate is removed, then it will become P plus jk. So angle will be reversed. Now delta I will become positive, delta k will become a negative, and theta ik will become a negative. So this is what my power flow equation. Okay, for I'm telling about for the two bus systems. So how we can write down for if I separate the real term and imaginary term. So this angle, suppose this angle is replaced by cosine, then that will become a real term. And suppose this angle is replaced by sine, then that will become an imaginary term. Okay, that is, we know that e raised to v at an or you can take x at an angle of theta is nothing but cos theta plus j sine theta. Okay, so in this form, so cosine term is the active power and sine term is the reactive power here. So vi yik vk cos of delta I minus delta k theta ik, and similarly imaginary power or reactive power is vi yik vk sine of delta I minus delta k minus theta ik. So suppose I substitute I is equal to 1, so this will become a P1, Vi will become a V1. So when k is equal to 1, so when the k is equal to 1, so this will become Vy11 V1, delta 1 minus delta 1 will be cancelled, so minus theta 11. So V1 square Y11 cos of minus theta I1. Suppose I substitute k is equal to 2, then V1 into V2 into Y12 cos of delta 1 minus delta 2 minus theta 12. Similarly can be written for the reactive power. Similarly for the burst 2 and burst 2 active power and burst 2 reactive power. Hope you got all these terms. Similarly, we will expand this for this is our system is not a two bus systems. We are having the n number of buses are connected together. So to form the n number of buses system connected together, we will assume that the loads as a negative generator, because they are taking consumes the power. So we take the load at the negative generator, means we are considering the active power. If it is a load bus, we are considering that is as good as a generator with a negative sign. So means it indicates that it consumes the power. So SI is equal to PI plus JQI, that is a VI into II conjugate, where I is from 1 to n because it is n bus problem now, where VI is the ith bus voltage and JI is the equivalent current injected. So PI minus JQI is equal to, if I take the conjugate of this term, so SI conjugate, then it will become a PI minus JQI. So it will become a VI conjugate into JI. So in the Y bus matrix, so we know that Ji is equal to k starting from 1 to n. Now I am taking this is up to n. So Yik into theta ik. So suppose I substitute the value of Ji, that is a summation from k is equal to 1 to n Yik Vk. After substituting this, so we will get this term. So but Vi is equal to Vi at an angle of delta I, and Yik is equal to mod of Yik at an angle of theta ik. Suppose I substitute this, then Si conjugate is equal to Pi minus Jqi. So Vi conjugate. So it is a minus delta I, Vi minus delta I. Yik is Yik at an angle of theta ik. Vk is mod of Vk into theta ik. So similar way, delta I is taken inside the bracket, so it will become a theta ik plus delta k minus delta I. Therefore, the complex power, so removing this conjugate, it will become P plus jq. So mod of Vik starting from 1 to n Yik Vk theta delta I minus delta k minus theta ik. So separating the real and imaginary terms, so we will get the one term for the real power and one term for the reactive power. Suppose we will expand for the self and based on the self and transfer admittance. So this is based on the self and transfer admittance. Ith bus power is taken from the this equation outside. So when the k is equal to 1 to n, but k is not equal to I, because when the k is equal to I, that term is already taken over here. So this equation same written here, only substituting I is equal to k, that equation is taken here. For similarly for the reactive power. So hope you got these answers. So here you can see that for each bus we have a two equation. For each bus we have a two equation. One is the active power equation and another one is the reactive power equation. So again we have a reflection point. So let's begin with the reflection point. For 5-bus system, number of non-linear equations formed by the power flow equations are 5, 8, 10, 2. Okay. So how many equations, nonlinear equations will be formed by power flow equations for 5-bus systems? So discuss, let's begin with the answer. Okay. So hope you guess the answer. Pause the video and guess the answer. Yeah. Hope you got the answer. So it is what? 10. So for the formula is what? 2n. 2n number of equations will be there, because one is for active power and one is for reactive power for each bus. So total number of buses are n, then it is a 2n. So total number of buses are 5, hence it is 10. Let's summarize all things together. Load flow is a static problem. For a particular demand, we are going to determine what is the power flow or load flow. Number of variables for each buses are 4, P, Q, V and delta. These are the 4 variables for each bus. Out of that 4 variables, there are the 2 known and 2 unknowns. Based on that, they are classified as PV bus, PQ bus and slack bus. In the PV bus, P and V is known, Q and delta is unknown. In PQ bus, PQ is known, V and delta is unknown. And in slack bus, V and delta is equal to 0, but P and Q are unknowns. Static load flow equations for 2-bus systems are 4. Okay, so if there is 2-bus system, the static load flow equations are 4. One is for active power and reactive power at bus number 1. Another is for active power and reactive power at bus number 2. So total 4 equations will be formed. And the static load flow equations for n-bus systems are twice n. So hope you got all the answers and you get the all information about the power flow equations, how these power flow equations are derived. Okay, so with this we are at the end of video. Hope you enjoy the learning. Thank you very much.